I'm Ralph Cavanna. Now, Amory is, as you all know, the fifth and final MING visiting professor on energy and the environment at Stanford. And so it is worth noting that we all owe debts of gratitude, in particular this evening, to the MING committee, led by Gil Masters, to Mike and Diane Ming, and to MAP, Mineral Acquisition Partners, led by Jane Woodward, for sponsoring all of the visiting professors, and specifically this lecture series. And we are also grateful to Stanford's Department of Civil and Environmental Engineering and to all the teaching assistants who've been so tremendously helpful for this class, as well as the evening lecture series, whose many contributions Amory has caused to appreciate even more than we do. And I want to assure all of you that he owes you lifetime letters of reference, and I will make sure you collect. For the last in my sequence of 5 introductions of Amory, I have chosen an excerpt from a 16-year-old article by Chip Brown, the winner of the National Magazine Award, which remains my favorite introduction of Amory. And I want to assure you that I'm reading verbatim and not embellishing. It goes as follows. Even at 27 pages, Lovins' resume doesn't tell the whole story. He composed his first piano music when he was 7, received a patent on nuclear magnetic resonance technology when he was 17, and did work reported in the Journal of Chemical Physics long before his 17th birthday. His car is white, which would save about 1/4 of the cooling load on the air conditioner if he had an air conditioner. One of the most frequently reprinted articles ever published in Foreign Affairs is Lovins' Energy Strategy, The Road Not Taken. The article went through at least 12 drafts. With a hurricane threatening to knock out power lines in Maine, Lovins stood in a phone booth near Camp Winona for 14 hours editing The Galleys. I know you can all visualize that easily. And then in closing, of course, telling America that it needed a soft energy path was the equivalent of trying to recast John Wayne as a hostage negotiator for the UN. But Lovins is undaunted. He insists, quote, "The energy problem is conceptually solved, although about 50 years of details remain. Stand by to absorb them all in the next 90 minutes. Amory Lovins."
Thank you, Ralph. After that introduction, I can't wait to hear what I'm going to say about the implications of advanced energy efficiency. Why would we do it? And just scratching the surface of its potential in this country, it's already done a lot. The green bar here shows how much energy we didn't use in 2005 that we would have used to run the same economy if we were still as inefficient then and had the same energy intensity as we had in 1975. And that was just slightly greater savings than the total energy use of Europe in the same year, and considerably more than the energy use of other major countries. In fact, it was also over twice our use of oil. It was about 6 times our oil output or our net imports from OPEC, and it was 13 times our net oil imports from the Persian Gulf. So if we hadn't done that reduction in energy intensity, the world would have been a whole lot worse. And if we got serious, we could, with further technical improvements in end-use energy efficiency, save over half our oil for $12 a barrel, roughly a fifth the recent price, save at least half our gas at under $1 a gigajoule, roughly an eighth the recent price, save at least 3/4 of our electricity at about an eighth the typical price. It's in fact cheaper to do that than just to run a coal or nuclear plant, even if building it costs nothing. We would correspondingly, of course, increase how much we could do with any kind of alternative supply. We would prolong cheaper options for supply, delay costlier ones. That is, in any form of supply, we'd stay on the lower, easier part of the supply curves. We'd rebalance supply and demand nicely, reduce volatility, gain spare capacity in case of supply interruptions. But indirectly, we'd have some other big benefits. We'd cut and stabilize fuel prices, especially for world oil, but also for gas. For example, I mentioned 2 nights ago that saving 1% of U.S. electricity, including peak hours, would cut natural gas use by 2% and its price by 3 or 4%. Certainly, any even expectation that the U.S. is about to save oil will soften expected oil demand and price with big benefits, especially for the poor countries that are most stressed by high oil prices, and also big benefits for stability. It is no accident that with isolated exceptions like Bahrain, the Arab countries that don't have oil have had more development success than the Arab countries that did have oil. We would get better energy services, and that extra value is worth a lot more than the saved energy cost. We would have a richer world, more fairly distributed, and by free market choices, we could, as I'll describe next, solve the oil, climate, and largely proliferation problems, all led by business for profit. We'd also enable renewable sources to do more sooner and cheaper, and most valuably, we would buy time to develop and to use better technologies, to learn more, to make smarter choices. Time is the most precious thing you can buy in energy policy. And I think altogether it's clear that advanced energy efficiency is the best known master key to many of the world's biggest problems, either unlocking them directly or showing a better way to think about other kinds of problems, like, say, water. You may ask, well, what happens if we have those wild successes? Won't that knock down the energy price and make what I just described uneconomic? Could oil get so cheap that those triple efficiency cars, trucks, and planes that I talked about 2 nights ago no longer pay? Well, no, because actually they're cheaper than any realistic oil price. They're on the order of $12, $15 a barrel, and their other attributes mean that manufacturers have to pursue them anyway for success in competitive strategy, regardless of oil price. Would people drive more when oil gets cheaper because we buy less of it? Well, yeah, but it's a small effect. We figure net it's about 1.5%. What about electricity? Well, cheaper power is even less likely to undercut efficiency because most of the price of electricity is a fixed cost from its extreme capital intensity, and that's already paid for. Not so much of the price of electricity varies if you use less of it. And in general, because it's cheaper to run a power plant, a thermal power plant, it's cheaper to save electricity than to run a thermal power plant. It really doesn't matter how many of them you have. If it's cheaper not to run them, you shouldn't run them regardless of your capacity position. So these kinds of reequilibration effects in the economy are real, but they're small, and they won't change the outcome that efficiency is still a great buy and will beat supply. So this suggests that the energy future is not going to be business as usual. On the whole, I think energy prices will become less important. Energy will become less predictable using economic tools and perspectives. And our major energy institutions will become less important to have. Capital is going to move a lot faster, as in many other areas of the economy. The emphasis will also shift from commodities to services, and an economically efficient carbon market will clear at very low prices. In principle, it should indeed clear at negative prices because you can do all of the climate stabilization you need if you really get good at it just with energy efficiency that's cheaper than the fuel it saves. And the outcomes are going to end up being driven more by the convergence of disruptive technologies and by innovations in competitive strategy than by new public policies, which will always be playing catch-up. Wholly new sources of energy are also possible, and there may be physics we haven't discovered yet, but even without that, just discontinuities and surprises are going to speed up. And also, probably some very bad things will happen. Just for example, 2/3 of Saudi oil, the only source of, so to speak, liquidity in the world oil market, flows through one processing plant that's already been attacked and two terminals, the larger of which has already been attacked twice. What part of this don't we get? And for the bad guys, successfully attacking those facilities would be a twofer. They could bring down the Western economies and the House of Saud at the same time. When bad things happen, there will be, of course, temptations for us to do stupid things. We've done it before. Now, I think also there will be a major shift, as I'll return to at the end, from north to south towards south to north, tech transfer and innovation. And leapfrog global development is going to be greatly facilitated by these technologies because they will, in particular, apply to rapidly growing economies. China and India come to mind, and will help them jump over the mistakes we made and only make interesting new mistakes, and will help them very much shift to renewables. There are some things we should have learned by now about sound energy policy. For example, it's not a Chinese restaurant menu where you pick one item from column A and one from column B and so on until you've taken some from every place and everyone's happy. And it shouldn't be an effort to achieve political balance between factions or between campaign contributors, you know, like the old recipe for elephant and rabbit stew, one elephant, one rabbit. It shouldn't pick winners. It shouldn't stomp on innovation. It shouldn't assume that efficiency may not work, so we need to buy all the supply we were going to buy anyway. That's a recipe for stinting both because they both compete for the same resources and getting neither. It's also a potential recipe for doing what we did in the early 80s. That's to get both, and that also bankrupts the suppliers because they need high demand to pay for their costly supply. Most of the energy policy disasters we've had so far in the first 30-odd years of energy policy as a discipline and practice have been caused by bad public policy, not by external events. These were disasters designed by committees and inflicted on ourselves. Many of us from a wide range of political perspectives, including my independent one, have come to feel that conservative free market principles really have a lot going for them in this context. I want to go through some of the implications of advanced energy efficiency in 7 categories. I'll start with oil. Oil prices have been perfectly random since oil was discovered. This is the Brownian motion that our friend Dick Holt in the Department of Energy accidentally came up with while trying to understand his charting program on his early model computer. And it's simply the year-to-year percent change in oil price with a 1-year lag between the axes. So if this were perfectly random, it would have, as it does have, a center of gravity at 0, 0. And if it had a secular trend, it would tend to cluster in one or another quadrant. All that happened after 73 is the volatility tripled. But the oil prices do satisfy every statistical test of randomness. Now, if you look at the history, you can see there was a very volatile period down back in the 1860s and 70s, and gradually things settled down. We had a very quiet, sort of aseismic period during the 50s and 60s. Then things went haywire, and now they've kind of become rumblingly volatile. Another way to look at that, which I kind of like, and notice the broken scale on the horizontal axis, is that if you plot world oil consumption against the real price of Saudi marker crude, and start back here in 1970, you can see that when oil prices were low, demand grew quickly. Then we had the Yom Kippur War, the Arab oil embargo, prices shot up, and then the next 5 years, demand grew more slowly until the Shah fell. And then with that Iranian revolution, prices shot up even more, so much so that demand went down. Notice it's going back towards the left, that's lower demand. So much so that meanwhile, all the supply expansions put in place combined with the lower demand to cause a glut, which crashed the price. And when the price went down over several years, the demand started to creep up again. It spiked a little when Iraq invaded Kuwait. There's 9/11. There's the invasion of Iraq, and you are now here. So what's going to happen? Could very high oil prices stay up for long? Could this glut and crash scenario recur? Well, what happened back then? Could we see that bad movie all over again? What happened was that in 1981, President Reagan came into office believing that the country needed huge expansions of the kinds of big, slow, costly supplies that had not been competing very well in the market. So he greased the regulatory skids, put in huge subsidies, and started to get a big expansion coming online of coal and nuclear and frontier oil and gas, except he didn't notice that meanwhile the market was quietly producing a gusher of efficiency under the twin influence of the Carter-era efficiency-oriented policies that were still working their way through and the 79 second oil shock. So you had these two trains rushing down the track in opposite directions. They met with an almighty clang in 1984-5 with glutted supplies, crashed prices, bankrupt suppliers. Cut 20 years ahead, another president came into office with the same belief system and put exactly the same forces in motion again with identical policies. Now, there are some differences. The efficiency drivers are a little different now, but arguably stronger. Less federal policy, more state policy, much more private sector initiative, more activity in civil society, more climate concerns, and so on. And despite those different details, efficiency is coming on impressively quickly. Over 3/4 of the increase in energy services over the past decade has actually been fueled or powered by reduced energy intensity, only 22% by increased physical supply of energy. So if you just read the statistics that are 99% about physical supply, and you don't dig behind them to look at the rest of it, you might be forgiven for not noticing 3/4 of what the market is doing, and that can cause you to make some mistaken investments. Now, the same underlying dynamic we saw in the mid-'80s also prevails, namely that fast technologies, things that deploy more like cell phones and less like building cathedrals, things that are bought by millions of distributed market actors, tend to get deployed and to grab the revenue streams before big, slow technologies requiring specialized institutions can get deployed. This time, however, there are two fast runners in the race, not one. Last time it was just efficiency. Now it's efficiency plus micropower. More about that later. So I think there's even a greater probability that the fast runners will get to the prize first, and the slow ones will not have the revenue to support the debt that they've incurred. So this train wreck that's kind of happening in slow motion will take a few years to play out, and we don't know yet whether it's going to offset any upward price pressures from oil depletion, insecurity, climate concerns, or whatever. But watch for these dynamics, and we've already had a little trial run in that investors already lost in this country $100 billion on 200 gigawatts of combined cycle gas plants that were built under the influence of disinformation campaigns to serve demand that didn't exist. The key difference, I think, between now and the mid-'80s is that this time it isn't just energy prices that keep our eye on the ball. So if the prices go down, maybe our attention wanders. This time we also have serious concerns about security, geopolitics, and climate. Those will not go away so readily. And that, I think, will help keep our attention focused no matter what prices do. Now, the U.S. oil problem is, in essence, very simple. We've simply been pumping oil longer and harder than any other province on Earth, so we're more depleted. So the next barrel costs more at home than it does abroad. And in a market economy, there are only three solutions. Their right names, which are seldom used, are protectionism, trade, and substitution. Protectionism means that you tax imported oil or subsidize domestic oil or both to distort their relative price so you don't notice that the imported stuff is cheaper. Because the market says buy the cheapest first, politics domestically tends to say buy the nearest first, politics often wins. Of course, it's a little hard to see how you solve the problem of domestic depletion by depleting faster, or as Dave Brower said, strength through exhaustion. And it's particularly dumb to subsidize domestic oil because that also suppresses its efficient use. But we've been doing a lot of that. Now, trade is another alternative. It just means you unsentimentally buy in world markets oil wherever it's cheapest, just as our competitors do. And you diversify supplies, you stockpile, you cultivate good foreign relations, trade relations, and countries like Japan and Germany that have no oil, of course, are very good at buying it and earning the money to pay for it. A third option is substitution, and that's really what I've been lecturing about here all week. That's how to do the same tasks by cheaper means than oil, and that offers all of the strategically important plays. The rest are much less interesting and give much less kind of disruptive competitive advantage at the level of the firm or the nation. Now, the peak oil debate that meanwhile enters into this is that some people who know a lot about oil geology are contending that world oil output is about to peak or may already have peaked, and they note correctly that there are suspicious jumps in declared Mideastern oil reserve just after OPEC changed its policy so that you'd get bigger production quotas and make more money if you declared higher reserves. And they also correctly point out that the global data on oil discovery are really a mess with all kinds of different dating conventions and reporting conventions. Now, my view of this is that nobody can know who's right about peak oil because about 94% of the reserves are owned by governments, not companies, and those governments either don't know or won't honestly say, in many cases, what they have. So it's indeterminate, but it doesn't matter who's right because we ought to do the same things anyway just to save money. It's cheaper to save oil than to buy it, no matter how much there is, and there are plenty of other strong reasons, starting with infrastructure vulnerabilities like the Saudi ones and our own, to worry about oil no matter how much oil there is or isn't in the ground. So I view this debate as a bit of a distraction from what we ought to be doing anyway, but if you want one more reason to worry about oil, you may like this one. I don't think we need more. Now, the conventional view in the industry, as charted by BP, for example, is that we've already produced about 1 trillion barrels of oil at prices ranging from a few dollars up to about $20 a barrel. And if you construct a supply curve with these blocks of how much oil is available to be extracted at what kinds of increasing real prices, you'd get something like this, going to more remote and less conventional and more kinds of synthetic crude and ultimately perhaps coal to liquids. And also as you go, you get more and more carbon intensive. For comparison, this little red shaded block here shows the International Energy Agency's estimate from last year of how much oil the world will need to 2030, and that its economic cost, if not inflated by monopoly pricing practices, would be in the probably low to mid-20s of dollars a barrel. Now, just for fun, I spliced into this graph another 3 trillion barrels of oil substitutions from the demand and supply sides that we worked out for the United States in winning the oil endgame, and I reported to you on Wednesday night. And notice how everything suddenly slides to the right when you add those 3 green blocks of substituting some saved natural gas, but not accounting for quite a lot of it. This only counts about a third of it. Doubling end-use efficiency, and advanced biofuels. And you notice that that makes this very carbon-intensive, expensive stuff slip off very far into the future, and you probably never get there because you're all on renewables by then. So that's one of the examples of why buying time is valuable. And obviously your competitive posture and your investment strategy will be very different if you see that world than if you see this world. So it's important to pay attention to all the competitors in the landscape. Now, the challenge for oil companies is Schumpeterian creative destruction, and the chairs of 4 of them at least, 4 majors and 3 car majors, have already said that we're starting the oil game, and many have added the beginning of the hydrogen era. And I think it's clear to many in the industry that oil is probably going to get uncompetitive even at low prices before it becomes unavailable even at high prices. Or as Sheikh Imani and others have famously said, the Stone Age didn't end because the world ran out of stones, and the oil age won't end because the world runs out of oil. Of course, there are important transitional product lines as biofuels are being used in Europe, and there are compelling arguments for switching your business model to providing mobility and access which customers want rather than selling liters, or for the auto industry, selling cars, and to do that before someone does it to you. The most interesting thing, though, that surprised many when we first pointed it out is that if you own a lot of hydrocarbons in the ground, you'll probably make more money even in a world that buys no oil. And the reason for that is that in general, because you can use hydrogen so much more efficiently than oil, you will make more money out of the hydrogen without the carbon than with the carbon, even if nobody pays you to take carbon out of the air. To put it another way, you'll make more money taking hydrogen out of your hydrocarbons in a reformer than putting more in a refinery. So in a world that is taking this journey beyond oil, your oil asset values may actually be sustained or increased. Now, let me switch to climate and ask you, how is climate protection like the Hubble Space Telescope? Anyone know? Oh, they were both messed up by a sign error, a confusion between a plus and a minus sign. You see, the political debate on climate is all about cost, burden, and sacrifice. But any practitioner will tell you that protecting the climate is not costly, it's profitable, because saving fuel costs less than buying fuel. Efficiency is cheaper than fuel. Somehow this got left out of the whole economic and political conversation, but it is the empirical experience of practitioners every day. And that is why many firms, whether or not they think climate is a problem, are busy protecting the climate to make money. Two of our biggest chip makers in the world have been cutting their carbon emissions 6% a year with very fast paybacks. DuPont set an ambitious goal that by 2010, they would have been improving their energy intensity 6% a year, shifting significantly to renewables, and they would cut their greenhouse gas emissions by 65% below the 1990 level. That sounds awfully ambitious. How are they doing? Well, by 2004, they were down 72%. They were producing 30% more output with 7% less energy, and they'd made $2 billion net profit on the deal. By 2006, that was over $3 billion profit, and they were at 80% savings, and still quite a ways to go. BP met its CO2 operational reduction goals 8 years early, at, they bashfully said, no net cost. I pushed a little, and they admitted rather sheepishly that they'd actually made so far $1.6 billion profit on the deal. GE has pledged to boost its efficiency 30% over a 7-year period to create shareholder value. Interface has already cut its greenhouse gas emissions by nearly 8% a year, 2/3 of it through energy efficiency. Texas Instruments' new chip fab being commissioned in Richardson, Texas, uses 1/5 less energy, 1/3 less water, and costs 30% less to build, which was why it was built in Texas, not China. So many other examples of this sort, but generally, while the politicians keep debating the costs, smart companies are racing to get to the profits before their competitors do. If these two parallel universes ever converge, it will make the politics a whole lot simpler. Politicians really like talking about who gets the profits rather than who has to pay costs. Of course, there are many ways to reduce energy intensity once you realize that climate change is not an inevitable side effect of normal economic activity, but just an artifact of energizing the activity in a way that loses money by not using energy sensibly. We can reduce energy intensity and therefore CO2 emissions by changing the composition of output in the economy, by more sensible land use, so you're already pretty much where you want to be and don't need to go somewhere else, by more mindful behavior, mindful markets, different lifestyle choices, and also by technical improvements in energy conversion and distribution and end use, which is the subject of these lectures. But I want to emphasize that all of these are big and important. For example, just cogeneration, combined heat and power, if thoroughly adopted, would about triple the total system efficiency of U.S. power plants, which have been flat for decades. It would save tens of billions of dollars a year. It would cut America's CO2 emissions by about 23%. Additionally, just using industrial heat several times, cascading it to lower quality uses, could save about another 11% of total U.S. energy use, essentially all from fossil fuel. So those are big terms left out of my end-use efficiency discussion, and they just add more profitable opportunity. Now, the canonical assumption by most economic forecasters is that the energy used to make $1 of GDP in the world is going to keep falling by about 1% a year. But if we could make that 2% a year, it would stabilize carbon emissions because together with decarbonization of fuel that's happening anyway, it would offset population and economic growth. And if we could boost that to about 3% a year reduction in energy intensity, it would fairly rapidly stabilize the climate and avoid whatever changes are not already irreversibly in train. Could we do that? Well, yeah, actually we have in many years under both high and low energy prices. California has done about 1 percentage point faster than that and cut its electricity use per person in half and its new house energy use by 3/4 already, and is still improving. China did better than that, cutting energy intensity over 5% a year for over 20 years, then almost 8% a year, till 6 years ago when they temporarily came off the rails. They'll probably get back on around this year. Attentive companies, some of which I've just named, profitably cut their energy intensity 6 or 8% per year. So what's so hard about 2 or 3? And since everyone else makes money on the deal, why should we assume from theory that this is costly rather than learning from experience that it's profitable? Now, I tried to show Monday through Wednesday nights that saving over half our oil and gas and 3/4 of our electricity is very profitable, even against short-run marginal cost. It turns out you get similar results in Europe, even though some countries there are, in certain respects, more efficient than we are. And the head of Tokyo University, a very good engineer, says he believes Japan can profitably triple her energy efficiency, which is already on paper quite good with the lowest aggregate intensity of a major industrial country. I think he's right. But I want to say a little more about the other 2/5 of the carbon problem. I've already talked a bit about oil, which causes 42% of fossil fuel CO2 release. Another 40% comes from powering thermal electric power stations. Now, there are two 1989 case studies that pretty much scope the range of the world's conditions. One was done by then the Swedish State Power Board, Vattenfall, which has since been more or less privatized. And that study on the challenge of choices for that cold, cloudy, northern, heavily industrialized, and relatively efficient country found that half of Swedish electricity could at that time be saved at less than 1/4 the cost of making more. And if you combine that doubled end-use efficiency with a little fuel switching, mainly in forest products industries, and with environmental dispatch, running most of the plants that emit the least carbon, you could achieve the forecast major growth in the economy, shut down the nuclear half of the power supply as the voters had demanded, reduce the heat and power sector's carbon emissions by 1/3, and cut the cost of electrical services by $1 billion a year, all at the same time. This report was not well known. In fact, it was not translated from English to Swedish for a long time. So some years later, the Parliamentary Energy Committee had never heard of it. It got fairly successfully suppressed by the Swedish nuclear lobby, but its logic remains entirely valid. Just the technologies have gotten a lot better since then. In India, the late Amulya Reddy at the Indian Institute of Science did a roadmap for the states of Karnataka. And in Karnataka, he found that a rather modest portfolio of efficiency and combined heat and power from sugarcane waste and biogas and so on, and a few distributed renewables, a far from comprehensive portfolio, could get much better, bigger, faster economic development than the government plan, and would use 3/5 less electricity, 2/3 less capital and total cost, and release 200 times less fossil fuel CO2. By the way, neither plan was implemented. Now, in both cases, the savings from substituting efficiency for fuel more than paid for any cost extra for the renewables. So the whole thing ended up better than free for achieving major carbon savings. Now, since then, technology and analysis have moved on, and an interesting recent example, which is on the Vattenfall website, is a global study by McKinsey looking at the potential for abating global emissions of greenhouse gases, or GHGs. The vertical axis here is how many euros it costs to abate a metric ton of carbon dioxide emissions or their equivalent in other gases like methane and nitrous oxide. The horizontal axis is how many billion metric tons of those emissions you could abate annually in 2030. And the total amount shown here, where the costliest abatements are below 40 euros a ton, is a 46% reduction. Now, it turns out that the first 7 billion tons of reduction has a negative cost. That's stuff like efficiency that costs less than the fuel it saves. Then they get into some other substitutions of supply and reforestation and so on that they believe are more expensive than what we're doing now. Some of these are a little odd, like industrial motor systems, which are shown as costing quite a lot. One of the more expensive measures, they're actually one of the cheapest, so I think they must not have taken a whole systems approach. And if you look more carefully at things like fueling efficient commercial and individual vehicles or air conditioning and lighting systems and so on, I think it's already clear that this is probably a rather incremental view with very old technologies and is technologically very conservative, not reflecting any of the whole system design that I've described earlier this week for transport, buildings, or industry. Nonetheless, it's interesting that the area under the negative cost part of the curve essentially balances the area under the positive cost part. So according to McKinsey's very conservative assessment, nearly half of the 2030 global greenhouse gas emissions could be abated at an average cost of 2 euros a ton, essentially free, down in the noise. So imagine what you could do with integrative design and modern technologies. It would all be negative cost to abate as much as we need to stabilize the Earth's climate. In fact, if you imagine an affluent world in 2050, say, with, say, twice as many people as we used to have a decade or two ago, and 3 or 4 times the affluence per capita, that's a 6 or 8-fold grosser world product. But meanwhile, carbon intensity falling as it has done historically by a factor about 2 to 4 over a half century as we substitute renewables and gas for coal and oil. And suppose that we got about a 50% gain in conversion efficiency by doing combined heat and power and running power plants better, combined cycle plants and so on. And most of all, suppose that we simply increased end-use efficiency by 2.8 to 3.6% a year. And the U.S. has already done pretty much around the upper end of that range without even trying. And suppose we got anywhere from no gain to a doubling of the human happiness and satisfaction created by each unit of energy services delivered, by getting more services we want, less we don't want, and services of higher quality. Well, if you do all the math, you find that you could have 1.5 to 12 times less CO2 emission despite a 6 or 8-fold increase in gross world product. That's a lot of flexibility. The future is not fate but choice, and we can exercise that choice profitably over a very wide range. What about China? Often raised at this point in the conversation. China has, at purchasing power parity, roughly 3 times US, 5 times Europe's, 9 times Japan's energy intensity. And then remember that remark by one of Japan's best engineers that Japan could profitably triple her energy productivity, which implies if China did that, she'd be almost 30-fold more energy productive than now. That would take time, but there's no reason that across the sea of Japan the laws of physics should change. Strong energy efficiency and leapfrog technology are China's top strategic priorities since mid-2005. The 11th five-year plan enshrines them as the most important element of development strategy. Of course, the mountains are high, the emperor is far away, so the weakness is getting policy from Beijing into field enforcement in all the provinces. But that's speeding up, and it's being pulled along by companies like Walmart that are giving preference in their purchasing, and they purchase 1/6 of China's exports to the U.S., to producers that have green and efficient practices. Now, China is, to be sure, still building many coal-fired power plants by default, by momentum. Most of them are not actually authorized by the central government. And a glut is rapidly emerging because that's combining with a lot of renewables coming online, wind, small hydro, and so on, plus Three Gorges, plus electric efficiency standards starting to bite. My own expectation is that their 30 gigawatt nuclear target will fade as they realize it's too expensive. Their 30 gigawatt wind goal, starting to exploit the world-class resource in Mongolia, will be readily exceeded. They're starting to adopt competitive wholesale power markets and more transparent decisions. Those things all argue in this direction. And really, the big problem is the rate of building very inefficient new buildings, many of them modern-looking, steel and cement plants, cars, machines for wasting China's energy, destroying wealth, destroying development prospects, and their paramount leadership understands this a lot better than ours does. They are desperate about not falling into the oil trap that we did, and we can expect them to act accordingly. Now, to be sure, they have recently, through habit and bureaucratic momentum, been investing about 20 times as much money in energy supply as in efficiency. That's backwards. And they're starting to realize they can't go on doing that. They pay 3 times the share of GDP for electricity that we do, for example. But China has also become a world leader in LEED Platinum buildings and in many other green innovations. Tom Friedman correctly says that green China is a much greater competitive threat than red China. We are the intended leapfroggee in their leapfrog development strategy. And you may be interested in some remarks I made at the end of a recent China-US climate summit in Berkeley. I told our Chinese guests, your society has 5 millennia more experience than mine. It has 5 times more brains and quite possibly better ones. About 90% of the technologies underlying the West's Industrial Revolution were invented in China. Your country is the only one on Earth to have cut its energy intensity over 5% a year for 24 years. It's the only one where energy efficiency is the #1 strategic priority. And although your energy policy framework is still in a fairly early stage of maturation, it has sounder basic premises than ours. You're executing it more vigorously, you're more highly motivated, you work harder. For all these reasons, I think we can rely on China to lead the world out of the climate mess. I'm not sure they'd heard that before. You may then ask, what about nuclear power? Well, first of all, just to make things really clear, it has nothing whatever to do with oil, because only a few % of our electricity is made from oil or vice versa, and only a tenth of that oil, that small amount, is actually distillate. Most of it is the gooey bottom of the barrel called resid. And most oil-fired power plants run briefly, but nuclear plants have to run steadily. Most oil-fired utilities are in places like Hawaii, where the grid is way too small for a nuclear plant anyway. You could, in principle, use nuclear to free up some gas to make electricity and then use the gas to substitute for oil, but that's a terribly expensive way to do that, especially when you can save half the gas at 1/8 of its price through efficiency. And there's just a much better and cheaper oil solution, which I outlined Wednesday night, saving half the oil through efficiency at $12 a barrel, replacing the rest with saved gas and advanced biofuels for $18 a barrel. Now, also, because power plants only release 2/5 of the CO2 from fossil fuels in the US and in the world, and all sectors approach can save 2.5 times as much CO2 as anything you can do just to electricity. But just to pay a little attention to what's happening to nuclear expansion, it is coasting to a halt. Both the installed capacity and the reactors in operation. In fact, I've just put in the latest 2006 data in these little dotted lines. They're right on schedule. Actually, the capacity and output went down a little bit in 2006 because, of course, of basic demographics. This is kind of an even age stand. There was a great burst of reactor construction, but this is the age distribution of reactors in the world. And they're starting to retire faster than they can be built. So to offset the planned retirements to 2015, 73 not yet planned, plus all the ones now planned, would have to be built. I don't know anyone who thinks that's possible. If China built all 32 new units that they very ambitiously have announced for 2020, the nuclear bureaucracy being their most powerful one, it would cover hardly over 1/10 of the plants reaching age 40 worldwide, which is the normal advanced retirement age. And therefore, the global nuclear capacity is about to start a long, inevitable decline just from age. This was how it was projected in Nuclear Engineering International in June 2005, and the actual number is a little worse than that little point. So if you look at the small, slow, we are told, decentralized competitors on the supply side, and you compare them to nuclear net additions, which were projected by the industry to follow this fluctuating line, but this is the actual point for 2006, you find a funny thing is happening. Wind is adding several times more capacity per year than nuclear. So is cogeneration, in fact, many times more when you properly include standby and peaking plants. Nuclear net additions are comparable to or less than those of geothermal biomass and small hydro, and in fact, they were nearly passed in 2004 even by the lowly and expensive solar cells. So if you add up all those alternatives, what do you get? Well, the upper graph here shows the low carbon or no carbon decentralized sources of electricity by electric output, and the lower graph by installed capacity compared to nuclear as a black line here. The data on the left are actual. The shaded ones to the right of the vertical line are industry projections. So you notice some funny things. That the tan part, the combined heat and power, which saves at least half the carbon because it's 2/3 gas-fired and very efficient, plus the distributed renewables, the colored wedges, all renewables except big hydro, add up to 1/6 of the world's electricity. But in 2005, they added also 1/3 of the world's new electricity. And in 13 industrial nations, these micropower sources provided anywhere from 1/6 to over half of all the electricity in those 13 countries. And in 2005, micropower added 11 times the capacity and 4 times the output that nuclear added. Notice this curve is rising rapidly, and nuclear is nearly flat. In fact, in 2006, it appears that the output actually exceeded nuclear's for the first time, and that already happened with capacity back in 2002. Now, negawatts, electric savings, are not shown in these graphs, but they're probably of comparable size. They might even be bigger. And that implies that micropower plus negawatts now have over half the world market in electrical services. And central thermal stations, whether nuclear or coal or gas-fired, have less than half. Why is micropower winning in the marketplace? Well, maybe because it costs less and has lower financial risk. This would help explain why it's essentially all financed with private risk capital, while there isn't a nuclear project being built on the planet that is so financed. They're only bought by central planners. So to test this hypothesis about lower cost, I've been looking at 2 things. One is global investment patterns in clean energy. There's a fellow named Michael Liebreich in London who tracks transaction by transaction, and he found that clean energy investments grew 80% in 2005, 43% in 2006. In 2006, they totaled $71 billion, of which roughly $56 billion was for equipment that provides distributed renewable electricity, up from $38 billion the previous year. That's getting to be a pretty significant market. And market cap, $154 billion for wind companies quoted on exchanges, $95 billion solar, and so on. $53 billion demand-side efficiency, by the way, and also rapid growth in the relevant market indices in Kyoto ratifying countries, but not in the few that didn't ratify. It's done over 80% better than the NASDAQ or the S&P 500. Not a bad deal. And this is, again, bottom-up transaction by transaction real data. And then I looked at the latest empirical data from the United States for what it costs to make or save a kilowatt hour and deliver it to your meter, either from remote resources, which require a delivery cost that I've deliberately stated low, or from on-site resources that are already delivered, so you don't need to pay that delivery cost. Your actual costs may vary, but I've done this on a fair apples-to-apples basis in a way that, if anything, favors central stations. Now, for central stations, I used the canonical MIT study, the best out there, from 2003. It bakes in whatever subsidies central stations already received, which were big. Nuclear was, by most reckonings, around 3 or 4 cents a kilowatt hour subsidy in those days. Several, like 4 or 5 cents, have since been added to that. the reserve margins are not counted, and they concluded that you could send out electricity for about 7 cents from a new U.S. nuclear plant, which means by the time it's delivered to your meter, it would approach 10 cents. They also said that there were uncertainties about this, and in fact, at the latest French price of nearly a year ago, you have to add another cent because the capital cost went up 20% since then. But the MIT study also said, well, if we had very large subsidies for initial plants, that could drive down the cost and the construction time and maybe even eliminate the capital market's perceived risk premium. And if we did that, then we'd knock a few cents off the price. Well, we're trying that experiment. Congress took that advice and essentially offered in August 2005 to subsidize the next 6 nuclear plants built in this country, if any, by what's equal to their entire capital cost. Standard & Poor's, however, promptly put out 2 reports saying this would not significantly improve the builders' credit ratings because most of the risks that the capital market is concerned about are still there. So I think even this heroic effort will have roughly the same effect as defibrillating a corpse. It will jump, but it won't revive. Now, if it did work, however, that would get us to nearly the cost of existing coal plants, but if you put on a really stiff, like $100 a ton carbon tax, you could get that up to almost where nuclear was, or the same for combined cycle gas plants. So the folks in Washington keep juggling the taxes and subsidies to try to get the market to give them the outcome they want. However, they may not have noticed that all of these kinds of plants now have less than half the world market in electric services because cheaper things are grabbing that market. For example, suppose that you take wind farms and you assume that they cost roughly the median that they cost over a recent 6-year period when costs were falling rapidly. In fact, so much so that the cheapest plants were less than half this cost. And suppose you firm up the wind with a backup supply so that it's dispatchable. You can have it any time whether the wind's blowing or not. So it's fully comparable to the central plants. And if you took away its production tax credit, you'd go from the blue bar to the gray bar. On the other hand, meanwhile, it's getting cheaper within one power plant lead time. And there are a lot of other renewables that are also clearly competitive because they're selling like mad. Now, cogeneration, whether garden variety or combined heat and power with also cooling in buildings, trigeneration, or recovered waste heat industrial, is even, in many cases, a cheaper option, paying more for gas than utilities do. And then if you are good at retrofitting commercial and industrial efficiency, that's often around 0 to 1 cent a kilowatt hour, as very detailed data reveal from actual utility programs. If you're not quite as good at it or do a lot of residential shell retrofits, it can cost a few cents a kilowatt hour. If you're very good at it, through integrative design, as described earlier in these lectures, you can often make it go to a negative cost. If you just sort of stand back and squint at this graph, it's pretty obvious the stuff in the upper left costs more than the rest of it, so you would expect that to be selling slower, and that's exactly what's happening in the world market. But this has a very interesting implication for climate change. I can take 10 cents, more or less, and invest it in a new delivered nuclear kilowatt hour. And I don't care whether the right number is 10 or 15 or whatever. The point is, it's a big number. So I will only get 1 kilowatt hour of coal-fired power displaced for my dime, if I'm lucky. But if I spent the same dime buying something cheaper, this other stuff, I would get 2 to 10 times more carbon displacement because I get more of the other stuff. That's what cheaper means, right? So if you buy something expensive instead of something cheap, you get less of it, and you also get it slower because nuclear builds slower than a lot of these distributed technologies that are distributed in market actors have very short lead times. And you know, if climate is a problem, we ought to be investing judiciously, not indiscriminately, and we ought to buy the most solution per dollar and the most solution per year. If we buy something else, we're making the problem worse than it should have been. That's called opportunity cost. You can't buy 2 different things with the same dollar at the same time, and if you buy one, you can't buy the other. For some reason, this rather important point has never been reported, as far as I know, in the financial and business press. Now, just as a little update, nuclear capital costs and fuel costs are going through the roof. the pre-MIT study simply quoted the industry's hopes and wishes and quoted each other. There wasn't really honest empiricism until the MIT study. And that evidence-based study derived roughly $2,000 a kilowatt. Some U.S. utilities are now getting much higher numbers. And it's interesting that historically, if you look at a ranking Jonathan Koomey and his colleague Dr. Holtman have done for all the 99 U.S. plants built, you find you'd have to be down among the very cheapest ones for the MIT All Goes Well or the University of Chicago study or the industry's claims to be valid. 8 recent Asian plants look way off the scale. They look to end up around $4,000 a kilowatt, somewhere up in here. Before recent construction cost escalation, the construction cost indices, given especially the Chinese run-up in demand for concrete and steel, have just been standing up on end lately. And meanwhile, there are looming fuel crises in nuclear, which always thought it had cheap fuel. And Jim Harding showed in a recent Euratom paper, Euratom anniversary for the European Parliament, that this would probably roughly double, triple, quadruple, maybe 7-fold increase, who knows, the nuclear fuel cost, depending on whether you require a very costly and silly thing called reprocessing. There are also big bottlenecks showing up in manufacturing. It's not clear the industry really has the capacity to make stuff anymore at any scale. So realistically, bus bar cost may just have gone up about 4 cents. And I just add that as a further cautionary note, but even using the MIT numbers, clearly there's a case to be answered. I mentioned earlier there's quite detailed data. This is a very small piece of that information about the cost of saving electricity. These are actual utility programs in California, and they fluctuate from year to year a bit as programs are turned on and off, because then if you start them up rapidly, you have a big admin cost to get going again before you get up to volume and get the cost back down. And there are some big numbers in here of programs. For example, this purple solid line represents 79 utilities programs in the Northwest. These numbers down here represent 237 utilities or utility programs by 58 companies. And there are many other multiples in here. So there's really a lot of well-measured data behind this. And in general, those utility programs don't dive nearly as deep as RMI's assessment of potential savings. That is, they tend not to do integrative design or the latest technologies. Nonetheless, in 1989 and 90, and in a joint Scientific American paper, the Electric Power Research Institute and Rocky Mountain Institute published their respective supply curve estimates. Actually, the EPRI curve doesn't show an extra 9 to 15% savings that they expected would happen anyway. 50% of use is up around here. So although the definitions are slightly different, these are both big, cheap savings, and it turns out the difference between them is essentially all methodological rather than substantive. The RMI estimates are based on measured cost and performance for about 1,000 technologies, very thoroughly documented in a bookshelf we wrote back in the late 80s, early 90s. And it was retrofittable technologies that could save about 3/4 of U.S. electricity at, in today's dollars, about 1 cent a kilowatt hour. Similar results were found by very detailed independent assessments in Europe, especially in more efficient countries. And of course, the savings have since, as EPRI will agree, gotten bigger and cheaper faster than we've used them up. I want to dig a little more into distributed generation by asking what's the right size for the job in supplying electricity. For the first century of this industry, power stations were costlier and less reliable than the grid. So it made sense to build a number of big stations and back each other up through the grid. But the last 20-odd years, that stopped being true. Power plants are now cheaper and more reliable than the grid. So if you want really cheap and reliable power supplies, you need to make the power at or near the customers. That's what distributed power is about. And the market has recognized the gradual supremacy, the emerging supremacy of distributed generation as various benefits we were getting from central plants saturated and even reversed. And that is why so many countries, including some very considerable industrial powers, now get a substantial fraction of their electricity from distributed resources, the ones that we are told are slow, small, uneconomic, and won't do much for decades. There are many technologies of this sort: engine generators, small turbines, microturbines, 4 flavors of fuel cells, all kinds of cogeneration from various resources, some of which are carbon-free or carbon-negative, heat-based cooling systems, solar thermal electric, solar photovoltaic, also storage technologies and the ability to scatter the stuff around the grid where it will do the most good. And the EPRI vision, which I think is a very nice one, of utilities' emerging distributed resources portfolio, has things like solar cells on your roof, wind machines, probably not on your roof, but maybe off in the backyard, or down the street or off in the bay on the delta. Smart end-use devices, all kinds of controls and communications, plug-in hybrid cars exchanging power with the grid, distributed commercial and industrial generation and storage, and dynamic operations of the grid. So this is all the stuff out at the customer end, and it can gradually come to dominate the grid. And of course, the progress has been quite impressive. And interestingly enough, just in California, if you add up, say, wind and solar at reasonable capacity levels, because the solar's mainly in the daytime and the wind's mainly at night, their sum in the right proportions beautifully matches the load shape. Wind power has 74 gigawatts installed worldwide through the end of 2006, growing 32% a year. The US lags, but is now doing a lot again. Quite a lot coming on in India and China. India is actually ranked 3rd or 4th in the world in the rate of adding wind power. Germany and Spain are each adding each year more wind capacity than the world adds nuclear capacity. Europe is expecting to beat its wind targets handily. Wind can be firmed up by conventional generation, hydro or otherwise, by storage, by dispatchable demand response, or of course by other wind machines somewhere else where the wind is blowing. Central thermal electric power also works very well, the troughs in the desert, for example, and new projects are under development now in at least 3 states because the economics are so good. Renewable energy costs keep going down, and there are many examples of breakthrough technologies that one or another inventor thinks that they can bring on that go well below the conventional cost projections. But there's also an analytic revolution that changes the game. And that's an Economist book of the year summarizing it called Small is Profitable. You can get that at smallistprofitable.org. We published it in 2002. And it organizes 207 so-called distributed benefits, hidden economic benefits of making electrical resources the right size, typically increasing their economic value by about a factor 10, although the exact numbers are very site-specific. And this approach can apply to many resources like fuel cells. It can make handmade fuel cells at high handicraft prices, cost-effective right now in many uses if you put them in the right place, use them in the right way. The same for solar cells, the same in spades for demand-side resources, although the book was mainly about supply. Where does this big tenfold or so value increase comes from? Well, the biggest benefits come from financial economics, which often increase value by about an order of magnitude on their own for renewables, half that for non-renewables. The next biggest category are electrical engineering benefits that normally increase value by about a factor 2 or 3, but a lot more if you have a congested distribution grid or you need premium power quality. Then there are about another factor 2 worth of miscellaneous benefits, more if you can use waste heat, and I'm not even counting externalities. For example, financial economics, the tools used to analyze financial portfolios, provide you with nice ways to minimize regret at what you did you wish you hadn't or what you didn't do you wish you had. For example, Tom Hoff has done a closed-form analytics solution saying that if you're going in typical conditions to put a generator at the substation to support it on the peak hour loads in the hot afternoons. If you were willing to pay, say, $1,000 a kilowatt for a 50 megawatt generator that took 2 years to install, you should be equally willing to pay $2,700 a kilowatt, 2.7 times as much, for a 10 kilowatt generator that you can install over the weekend, because they will have identical financial performance. In other words, small, fast stuff is more valuable than big, slow stuff, and it's worth paying more for to get the same financial performance. You can also redeploy those resources. You put them where you think they'll do the most good, but if the system evolves in a different way than you expected, you can take them down, stick them on a truck, and put them where you wish you had. So you're more likely to get bigger expected benefits, double whammy. You get rapid learning and mass production economies of scale. And of course, renewables give you a constant price. Once they're installed, they're not subject to fluctuating, say, natural gas prices. And that can roughly double the present value you have to count in a cost stream for a gas-fired generator when you're comparing it with a wind generator, which doesn't have price volatility. So that means the wind generator is worth probably 1 or 2 cents a kilowatt hour more than you thought. And utilities are just starting to use those risk-adjusted discount rates, which any first-year MBA student knows about. We didn't do that in the first $1 trillion or so of utility asset acquisitions. There are also good reasons that come out of portfolio theory why you should buy a substantial fraction in renewable resources, even if they cost more. It's the same mathematics and reasoning that says you should have some riskless treasuries in your financial portfolio, even though they yield less, because they'll improve overall risk-reward ratio. There are also important synergies between efficiency and renewables. A house that doesn't use much hot water, because it has very efficient shower heads and so on, gets more, in my case 99%, of its hot water with a small solar collector. So it needs little or no backup. An electricity-efficient house, like mine, needs only a few square meters of solar cells to run it. That's cheaper than connecting to the grid a few meters away or already attached to the house. A passive solar daylit building doesn't need much electricity, and it can pay even for things as costly as solar cells by downsizing or eliminating mechanical systems. And if you bundle those kinds of efficiency or renewable options together, you get greater total effect at lower average costs, as in the 4 Times Square building in New York, where a 40% energy saving and was able to downsize the mechanicals enough for putting in fuel cells and shell-integrated photovoltaics on the south and west spandrel at no extra cost. So they were able to recruit premium tenants at premium rents, partly because it's such a pleasant daylit space, and partly by saying, well, don't worry if something goes wrong with the power supply. We have the 2 most reliable known power plants right in the building. And the total construction cost came in exactly at market average, but the market performance is a lot better. Here's a California example. You know, we build a lot of jails, and here's one in Alameda County, Santa Rita Jail, which happens to have 3 acres of photovoltaics added on the roof, but first they made the roof white to reject solar heat and made the jail more efficient in its air conditioning, lighting controls, so that on the hottest afternoons, when the solar cells are cranking out the most power, the jail isn't using very much, so it has the most surplus left to sell back to the grid at the best price. And that means it pencils out even without state subsidy. As it is, a $9 million project received $5 million of that back from the state for the efficiency, load management, and photovoltaics, but it would have worked even without it because the gross savings were $15 million. And they easily beat the county hurdle rate. Well, if that worked for solar cells, it will work for any other kind of micropower that's even cheaper. Of course, there's always a risk that whatever option you buy, it won't work. You'll have a dry hole. So what can we learn from actual market behavior about that? Well, in California from 1982 to 85, we had a pretty level playing field in letting supply and demand side options compete at fairly equal subsidies. At that time, the state's peak load was about 37 gigawatts. In just those 4 years, on this fairly level playing field, the utilities bought or were offered new supply and efficiency and most of the supply renewable, equal to 143% of their peak load, with another 25% a year arriving in new bids. And they had to suspend the bidding in '85 because if they'd kept it up for another year, they would have displaced every coal and nuclear plant in the state and had to shut them down. In fact, every fossil and nuclear plant in the state, which, in hindsight, might not have been such a bad idea. Maine similarly grew its non-utility generation from 2% in '84 to 36% in '95, over 2/3 of it renewable. There are other utilities that issued requests for proposal to see who wanted to offer them new supply, generally distributed, often renewable, in the 1980s. And on average, they all got offered 8 times as much of that alternative as they wanted and at far lower cost than they expected. So that's all with 20-year-old technology. Today's is a lot better and cheaper. And I think the lesson of that is if you really let competition rip, you're going to have too many options, not too few. Of course, the ultimate size of the alternatives also dwarfs that of, say, nuclear. Whether you believe EPRI's numbers or mine, the end-use efficiency potential cheaper than running and delivering power from a thermal plant is several times nuclear's market share of 19%. There's about as much cogen potential just in industry untapped in this country as nuclear capacity, not even counting buildings. The wind potential is at least twice U.S. or Chinese energy or electricity use. In fact, by some reckonings, it's a good deal bigger than U.S. total energy use. 6 times UK electric demand, 9 times global electric use today. Other renewables, even bigger. Land use and other such limitations are not an issue, but what some people are worried about is what do you do when the wind doesn't blow and the sun doesn't shine? Because that's real. Well, some renewables, those 2 in particular, are variable, although there are many others that are not or are very predictable. You can get tidal current tables 100 years out if you want. But the variability gets a lot less if you diversify sources because the weather patterns bad for one kind are good for another. And if you diversify sites over a range of hundreds of kilometers, the wind's always blowing somewhere. And you can forecast variability. We call it weather forecasting. It works very well. We do that for rain now in hydro systems. You can also integrate these variable resources with existing supplies and with demand response, especially if you have a smart grid. And when you add all that up, the variability of solar and wind power turns out to be less of a problem than the intermittence of the big thermal plants that we already built, because we've already bought enough backup for their tendency to fail completely from time to time than we would need to handle even, say, a very large fraction of wind in the grid, and you only need the backup once. Energy security then raises that other set of questions, and I think we need to be careful of the fallacy of saying baseload plants, meaning big thermal plants. Baseload has other meanings in utility economics that lead you to quite a different conclusion. Now, if I were to tell you that a lot of people make phone calls, so we need huge telephone exchanges full of relays and copper wire, you'd say, where have you been lately? We do a lot of that now with distributed packet switching. Or if I said many people use computing services, we need more giant supercomputer centers where you come submit your job to the high priest who will run it on the machine and tell you the result. You'd think I was barking mad. No, we do that stuff with network PCs now for the most part. And yet we still have the same mentality in the power business, even though a 1,000,000 kilowatt unit or 1,000 1 megawatt units or a 1,000,000 1 kilowatt unit all send out the same electricity. But in practice, many small units are actually more reliable than a few big ones, even if they're all equally reliable per unit. The reason is that the small ones don't all fail at the same time, and they are closer to the customer, but 98 or 99% of power failures originate in the grid. So if you bypass the grid and your power is local, you're a lot less likely to have the lights go off. And by the way, thermal plants are not at all immune to losing power on a large scale for an extended period. The average nuclear plant shuts down in this country for 37 days every 17 months, usually for refueling. But also you can have many units fail simultaneously without warning. Renewables don't do that. For example, in the Northeast blackout in 2003, We had 9 U.S. nuclear units in the Northeast that were working beautifully, 100% output. When the blackout came, they all instantly turned off. They have to for safety reasons. But then because of nuclear physics issues like xenon and samarium poisoning, you couldn't start them right back up again. They were guaranteed unavailable when most needed. This is an anti-peaker attribute. And it took 2 weeks to get them back. Over half the capacity was out for 12 days. That's not a desirable attribute for energy security. And in fact, if you look at the world after 9/11, you remember about the importance of resilient system architecture. The lights were routinely on 10 August 96. 35 seconds later, after some bad things happened in Oregon involving a tree limb and operator mistakes, 4 million unhappy campers in 9 western states and parts of Canada. Or in the August 2003 blackout, 71 gigawatts went dark in 9 seconds in areas containing 50 million people. But notice what stayed on, not just what went off. There were a lot of islands of light out there that had islanded distributed generation. And either they were set up to be able to cut loose from the grid and keep running, or they just did it anyway and broke the rules. And a lot of them were things like hospital backup generators, municipalities where a smart operator said, I don't like what's coming at me, I'm going to get out of this, and I have enough supply to run my demand. And there are ways now to prevent blackouts at a profit. The major failures that through accident or malice are now inevitable by design can be made impossible by design. End-use efficiency, demand response that can also ensure against price gouging and stabilize electricity and gas price, distributed generation designed for islanding and able to nucleate faster restart if it happens that you have a big blackout. All those options are cheaper, faster, more beneficial, more resilient. They're ample to do the job. They're a lot cheaper than, say, new power lines and power plants that actually make the problem worse, and they keep more money in the local economy. Unfortunately, our federal government that decides where to build power lines is still not allowing these options to compete fairly, neither are power pools in general, but I think that will change. And we can redesign over-centralized energy systems toward resilience. I did a study on this for the Pentagon back in the early 80s and described the design elements of a resilient system that makes major failures impossible. This description will be familiar to any of you that do resilient systems engineering in electronics, in military, in aerospace, and so on. And exactly the same criteria apply in energy. They make sense, they make money. Efficiency among those options gives the most bounce per buck because the failures it can't prevent, it makes happen slower and more gracefully and more fixably. It buys time to arrange substitutes. It stretches the fraction of demand they can meet. For example, if you have a tripled efficiency vehicle fleet, it'll triple your oil stocks effectively. And the half-filled tanks of those vehicles can run you around for 3 weeks. It's like a distributed strategic petroleum reserve. And the wellhead-to-car buffer stocks could last not for days or weeks, but for months to buy time to fix the system or improvise around it. Electric efficiency does the same by stretching the effect of distributed resources. Just a word about nuclear proliferation. There are a lot of issues around nuclear power that investors and the public are concerned with. And this is, by the way, a summary by a major advocate of nuclear power. Of these, I would say that proliferation of nuclear bombs and vulnerability to terrorism are serious issues and quite intractable issues. But notice that I've considered economics first. So those kinds of issues are not a minor counterweight to enormous advantages of nuclear power. They're rather a gratuitous supplement to its enormous disadvantages. And if nuclear power is, as I think the evidence shows, unnecessary and uneconomic, we don't need to debate whether it's safe. We just shouldn't do it. So its market failure, its dying of an incurable attack of market forces around the world, is a good thing for climate and security. It frees up money and attention for better alternatives, which, as it happens, takes about 10,000 times less capital than expanding the supply of electricity. 1,000 times less capital per kilowatt for efficiency, than 4 new power plants and grid, and you get your money back 10 times faster. Intensity times velocity is 4 orders of magnitude capital saving, but the power sector eats a quarter of the world's development capital. So you could reverse that and turn the power sector from a black hole for capital into a net exporter of capital to fund other basic development needs. You get, as I described earlier, 2 to 10 times more climate solution per dollar, and you get it faster from micropower and megawatts than from, say, nuclear. And also, if you recognize what the market's done to nuclear power, you're stopping the main facilitator and the main source of innocent-looking civilian disguise for the spread of nuclear bombs by countries like Iran and North Korea. Because it's really nuclear commerce that makes widely available in innocent guise all of the key ingredients for do-it-yourself bomb kits. Without nuclear power, those ingredients would be harder to get, more conspicuous to try to get, and politically much costlier to be caught trying to get or supply, because there'd be no ambiguity about it anymore. The reason you want them would be unambiguously military, and you couldn't pretend, as Iran does, that we're just making electricity. So a world without significant nuclear commerce would make proliferation not impossible, but a lot harder, and easier to detect timely because we could focus scarce intelligence resources on needles, not haystacks. Obviously, if a country like ours, with all of our financial wealth, technological prowess, and fuel resources, says we can't make it without nuclear power, that sets a very bad example for everybody else without those advantages. And I'm sorry that our country is currently leading in the direction most harmful to our security. In fact, the biggest threat to our energy security is our national energy policy. It perpetuates our expanding oil dependence in many ways. We thoughtfully bailed out the bankrupt Iranian and nearly bankrupt Saudi treasuries and empowered Ahmadinejad and Chavez and Putin. These are folks of our own creation, essentially. We're funding both sides of the war and losing a lot of moral stature in the process, and as Secretary Rice says, warping our foreign policy and various diplomatic postures and attitudes, weakening the competitiveness of our economy and making ourselves more vulnerable and fragile in many ways. But also, our energy policy strongly favors the over-centralized system architecture that showed up in Hurricane Katrina, for example. I had said in Brittle Power that a handful of people could turn off 3/4 of the oil and gas to the eastern United States in one evening without leaving Louisiana. Sorry if Katrina read that. And electricity, where we're finding regional blackouts getting more frequent and more intense, and our response to that is to do exactly the things, building more big power plants and grids, that make regional blackouts more frequent and more intense still. We are creating fat new terrorist targets, often upwind of our cities, and attacking those, by the way, is a major tactic of insurgents in Iraq, starting also in Afghanistan, may come soon to a theater near you. The centerpiece of our national energy policy is still to create a new all-American Strait of Hormuz on the northern slope in Alaska, when one Strait of Hormuz is quite enough. And since the President has correctly identified the spread of nuclear weapons as the gravest threat to our national security, I find it odd that he's trying to accelerate all the causes of nuclear proliferation and to intensify it further by trying to revive a totally uneconomic, waste-complicating matter called reprocessing. Now, if these are not the desired outcomes, I think it's the duty of our military and security professionals to say so. Some of them agree with that, and I think we will hear more from them in the months ahead. Finally, a little on global development. Think about a compact fluorescent lamp. It costs a few bucks. It saves 4/5 of the electricity used by an incandescent lamp. It lasts many times longer, looks the same, fits the same. There are many, many kinds, over 1,000 kinds on the market. You see better with it. You can screw it in yourself. It saves tens of dollars more than it costs. It's cheaper to give away than to run a thermal power plant. It keeps out of the air over its lifetime about a ton of CO2 and other bad stuff. You can use compact fluorescents to cut by a fifth the evening peak load that crashes the grid in many developing country cities. You can use it to raise the profits of a North Carolina chicken grower by a quarter, or to raise a Haitian family's disposable income by maybe as much as a third. It's the key to affordable solar power for poor households. where, for example, with such light, girls can learn to read, advancing the role of women enormously. China is the leading producer. They passed 1 billion units a year in 2003. Next thing, even more efficient light-emitting diodes, often also Chinese, evolving very rapidly, make solar power even cheaper to bring light to the world. So we can make the world safer one light bulb at a time, and you really can get it down at the corner shop and screw it in yourself. Leapfrog development, I think, can emphasize lighting and cooling to free up capital for other development needs through that 10,000-fold capital leverage that I mentioned a minute ago. And in fact, more broadly, advanced resource efficiency is the cornerstone of the development process, because otherwise the supply side eats the budget and you don't have enough money left to build the things that were supposed to use the energy. There was a famous episode in China told to me by a member of the State Council where China bought over 100 refrigerator factories to increase the ownership of refrigerators in Greater Beijing from a few percent to over 60% in just 6 years. They thought that was a really successful project, except the units were very inefficient. And this caused shortages of power and capital. So they learned from that they can't afford to develop unless they do it efficiently the first time. A very important lesson. So, as Ørenogo in Denmark says, by systematically pursuing the kind of advanced energy efficiency potential I've described this week, it's possible over a half century to offer everyone on Earth a joyful and materially decent life with a per capita energy consumption only a small fraction of today's consumption in the industrialized countries. That's a worthy goal. It's a feasible goal to have enough for all, forever, taking nothing, wasting nothing, doing no harm. The practical keys to doing this come from design. To get no inefficiency, we need no muda, no waste, purposelessness, and futility, no rules of thumb, no infectious repetitis, no incrementalism. We need to optimize whole systems for multiple benefits, bust barriers, reward what we want, commit ourselves to faith, hope, and clarity. The greatest of these is clarity, and relentless patience to push through changes that take a half century. This cornucopia that I've been describing to you this week is the manual model. We do actually all have to go out and turn the crank. And as St. Francis of Assisi said, preach the gospel at all times. If necessary, use words. There's a lot of practical works to be done as well. The central paradox here is that to think outside the barrel, we have to unlearn a lot that we thought we knew. We can capture enough efficiency to solve many of the world's biggest and most dangerous problems at a profit, because most of the world's energy is wasted, and the amount that's wasted that we could recapture and turn into profits keeps getting bigger and cheaper, but most people don't know this yet. Many even deny it on principle. This is a big barrier to action. You can't do something you don't think exists or is possible. So the biggest and cheapest and fastest and most benign energy option we have remains the most invisible, misunderstood, ununderstood, and neglected one. And yet, I dare to think we can change this, partly because the search for intelligent life on Earth is turning up promising specimens. You see, brains are evenly distributed, one per person, so they're mostly in the South. Half of them are in the heads of women, and many people who have not had much voice in the global conversation are getting hooked up to the emerging global nervous system, starting to have more voice, contribute their ideas. This is good for a lot more, you know, than spreading darkness with the speed of light. Because as far as we know, there's nothing in the universe so powerful as 6 billion motivated minds wrapping around a problem. So I think there's a huge potential here for south to north discovery, leadership, teaching, if we in the north have the humility to listen. Someone asked the late Dana Meadows, do we have enough time to turn this around? She said, we have exactly enough time starting now. David White has a poem about this. He says, this is not the age of information. This is not the age of information. Forget the news and the radio and the blurred screen. This is the time of loaves and fishes. People are hungry, and one good word is bread for 1,000. So what are we waiting for? We're the people we've been waiting for. If anything I've told you seems too good to be true, I'd ask you to reflect on Marshall McLuhan's remark that only puny secrets need protection. Great discoveries are protected by public incredulity. It's your move. Thank you.
I'll begin by merging two questions at opposite ends of a scale of magnitude. One, I would like my financial investments, retirement savings, to help solve the problems you've discussed. Where should I invest? And another customer at the other end of the spectrum asks essentially the same question about the $300 billion in the California public employee pension funds. What do you think?
CalPERS is becoming a leader in many kinds of green investment, and I think is giving a lot of thought to how to put more of it into energy efficiency. So I would urge you to encourage that. The same for private pension funds. There's a meeting going to take place, I believe, 13-14 April in New York, where many of the leading financial institutions will get together, led by Dan Reicher, now at google.org, to figure out how to get much more capital flowing into energy efficiency. Clearly, it has the biggest opportunities and is the most relatively undercapitalized part of the energy sector, offering the best returns at the least risk. So there's a puzzle there that I think some of the best financial minds are about to help sort out. And I'm told in the past month or two, there's been a huge growth in interest in some of the top financial institutions in the country in actually making this happen.
Amory, you touched on the issue of biofuels a number of times over the last 5 days. Two sources of concern. One, trade-offs between energy and food, particularly in developing countries as ethanol production expands, and possibly unintended consequences of unleashing digesting enzymes for cellulosic ethanol. Either or both worthy of concern?
Yes, if we did biofuels in a stupid way, as some people are doing with palm oil, it could cut down a lot of rainforests. I don't think Brazilian cane ethanol is likely to do that. The cane simply doesn't grow where the rainforest is. But you may have noticed that the kinds of biofuel I was talking about for the United States do not need any cropland. They would use, for example, switchgrass, miscanthus, crop and forestry wastes, but you could actually do the job just on conservation reserve land, which we plant typically to shallow-rooted annual crops to hold down soil erosion. Obviously, 2 or 3 meter deep roots on perennial prairie grasses, especially in polyculture, would do that job even better and could be done in a way that requires no inputs. The digestive enzymes, I think, could be of concern, and any genetically modified organism needs to be handled with great caution. There's a good reason that evolution didn't already produce it. So this is, I'm afraid many of the people in the biotech business have not adequately studied evolutionary biology and ecology, or they wouldn't be trying to do some of the things that they do, because Darwin always beats Descartes.
Amory, on the issue of California's efforts to limit its global warming pollution under AB 32, which I know you followed, any early advice? Should we be moving to a cap-and-trade system in California on CO2, and what other priorities would you assign to next steps?
That sounds like a good idea, and it could certainly help to pilot a national program. California leads in so many respects in energy policy. I don't see why this shouldn't be another one. The kinds of efficiency initiatives, the biggest on earth as far as I know, that are now underway in this state will have enormous repercussions, and I think are about to elicit much more industry leadership. I was pleased to read in the paper today that the province of Ontario is joining with both the Northeast and the California-led climate consortia to develop better policies there, and that's a major source of coal emissions.
Amory, moving to a local matter, you have noted that Stanford is undergoing a building boom all around you. What is your view of the quality of the architecture and design that you see emerging?
Well, I'm impressed by the team and the ambitious goals for the new Phil Knight Business Center at the Business School, and in a spring project course that will be launched next week, some of the students in my current course, of which these lectures are a part, will be helping that design team make it the best building it can possibly be and figure out how to apply its lessons more broadly across campus, both new and retrofit. So I think there have been a lot of lost opportunities in the past, and I hope that those will not continue and that this campus will quickly become as exemplary in that regard as it is in so many others.
Is there a political leader, either domestically or internationally, who, in your view, gets it with particular force?
Hey, I'm sorry.
Is there a political leader, either domestically or internationally, who, in your view, understands the points you're making in a particularly vivid and effective way?
There are some, and it's difficult for me to name them without its seeming to either make a partisan comment in the U.S. one way or another, because they're in both parties, or to meddle in somebody else's political affairs. My institute is scrupulously apolitical and nonpartisan, but it is clear from my work in about 50 countries that there are many leaders now who get it, and I think voters are starting to pick those out.
Well, then, Amory, three different members of the audience, since you won't answer that question, want you to answer this one, which is whether you would consider holding public office of any kind yourself.
No, I was actually informally sounded out once on whether I'd like to be Secretary of Energy, and I said only if you'd allow me to abolish the department and start over. And that was, and what I meant by that is that it has this contradictory dual role where most of its function has been building nuclear weapons and dealing with cleanup around them, and that very much distracts it from its civilian energy mission. So I'd like to get those activities out of the building into other civilian agencies and just focus on an unclassified energy civilian mission. And I think structurally that has to happen for the department to be effective. But I think I actually probably have more influence with fewer complications doing what I'm doing now at Rocky Mountain Institute than holding any kind of political office.
And in that spirit, I thought I would share with all of you one sentence, which I would not deem for a minute adequate to sum up the last 5 days, but it is the final sentence in Brittle Power, which Amory has been quoting from at length, only he didn't quote this. So let me. It is better to strive with all our hearts to achieve a future that may seem too good to be true than to continue to drift towards a future that is too dreadful to contemplate. Perhaps we could let that sum up this evening with our thanks to you, Amory.
And to you.
Well, so I'm sorry. First of all, would you, I think that's a good way to close. Thank you, Amory.
And because Ralph is too modest to do so himself, let me thank you for being the most wonderful MC I've ever had, and I hope we will see a lot more of you in this role.
Very good.